Which is faster on an 8-bit computer, BASIC or assembly? In this second video in our 8-bit Shootout series, we are going to pit the Commodore 64 against itself. I'll take you through how each program works and explain what's going on and why. So let's get started. I'm Timmy, and this is 3 Old Tech Dudes. In our 8-bit Shootout video, we wrote the same basic programs on 3 classic computers, then put them up against each other to see how fast each computer's BASIC interpreter could execute the program. It involved loading up a random BASIC array with 50 numbers and then running through a bubble sort to put them in order. Going into that video, I had no working knowledge of assembly language for any computer architecture. However, we really wanted to tackle at least one task on each of the computers in that video in both BASIC and assembly. Based on the wealth of information I found online regarding the platform, and since I had the programmer's guide for it, I chose the C64 as the first computer to make the attempt on. I initially wanted to fully replicate the bubble sort algorithm I wrote in BASIC for the original 8-bit Shootout video in 6502 assembly. However, it quickly became very clear that this would be a rather complex task for a beginning 6502 assembly programmer, at least as far as replicating the program behavior in exactly the same way, taking normal decimal numbers and sorting them from 50 to 1. I have learned how to sort hexadecimal or base 16 numbers in memory using 6502 assembly, but that's really beyond the scope of this particular video. We may dig into that more down the road here on 3OTD. So for this video, here's the task wheel test in our C64 BASIC versus assembly competition, counting from 0 to 100,000, displaying each increment on the first row of the display as it counts. How much faster is assembly versus BASIC at this task? As mentioned earlier, it's common knowledge that BASIC programs execute more slowly than machine code, but just how much faster can this task be accomplished via an assembly program? First, let's take a look at the programs themselves. We'll start with the BASIC program. This is a pretty straightforward CBM BASIC program. Line 10 clears the screen. Line 20 initializes a new integer variable count to 0. Line 30 sets up a for loop, which runs every line of code between 30 and 90 over and over, incrementing our count variable by 1 each iteration of the loop until count is equal to 100,000. Lines 40 through 70 set up some memory locations for the C64's plot routine. Line 40 sets location 781 to 0, which is essentially setting the X register of the processor to 0. Line 50 sets location 782 to 0, which is setting the Y register of the processor to 0. Line 60 sets the SP status register to 0. Not sure what that means, but it doesn't work without it. I found an old Usenet posting from 1994. I think it may be setting the processor stack pointer to 0. We will discuss these registers more while talking about the assembly program. Next, line 70 calls the plot routine, which utilizes the values set in 40, 50, and 60. Line 80 prints the value of count to screen. It induces a space to the left of the number, which you will notice when we run the program. Line 90 jumps us back to line 30 until count is equal to 100,000. And 100 is pretty self-explanatory. Now let's move on to our assembly program. Assembly is a whole different planet from programming as most developers know it. You have to have at least some understanding of the architecture of the processor and the hardware attached to it that you're attempting to write a program for. Unlike a high-level or mid-level language like BASIC, you cannot simply easily write a program in assembly language that loops a variable from 1 to 100,000 and just prints it on the screen. I initially attempted to write something using the processor's decimal mode, but as a beginner, this, much like the attempt at bubble sort mentioned earlier, became more complex than I expected, particularly when trying to figure out how to get what was happening in RAM onto the C64's display. Instead, I opted to think outside the box. Well, for me anyway. To explain what I mean, we need to understand some basics about the processor and display chip the C64 utilizes. Let's start with the processor. The Commodore 64 utilizes an MOS 6510 processor. This processor is in the MOS 6502 processor family and utilizes the same opcodes as the original 6502 processor. The 6502 and its derivatives have been the brain of some of the most memorable home computer and video game consoles in history, including all the 8-bit Atari consoles, the Nintendo Entertainment System, all Commodore 8-bit computers, Atari 8-bit computers, and many more. The 6510 uses the same opcode set as the 6502 in assembly language, so I will refer to the processor as the 6502 from here on out. There are some basics we need to understand about the 6502. There are 3 registers you can manipulate. The accumulator, which is considered the most important register in the processor, and the X and Y index registers. There are a few things you can do with these registers. This isn't an exhaustive list, but for explanation purposes in this video, we need to know the following. You can load these registers directly with single bytes of data in hexadecimal form from your code. You can load them with hex data from memory addresses in RAM. You can increment and decrement the X and Y registers by 1 with a single command. You can use the X and Y registers to assist in reading and writing bytes into memory. The accumulator, or A, is kind of a variable in its own right, but you cannot increment or decrement it directly like you can X and Y. Basically, you load A with a byte in some manner, and then assign A to other places, single byte locations in memory usually. 6502 assembly is made up of 56 3-letter commands. They aren't really self-explanatory based on the 3-character instructions until you learn about each one. We're not going to examine all of them, obviously, however, we will take each one as we come to them in our program. Let's talk about our basic design theory. Like our basic program, our goal is to display 1 to 100,000 on screen. I opted to utilize a single byte for each place value, essentially treating 6 bytes of memory as variables that directly relate to each place value, then increment each individual place value by 1 with my logic. When each place value reaches 10, we reset its corresponding byte to 0 and increment the next place value. We repeat this logic all the way until we reach the 100,000th place value. If that one is equal to 1, the program is complete and it exits. To make sure my logic would work, I tossed together a quick program in one of the many other languages I'm more familiar with, my old high school friend, Quick Basic. Actually, I utilized QB64, a modernized cross-platform implementation of good old QB. After a test run, this verified that the basic logic theory should work in assembly if I could manage to form the decision logic properly. Okay, let's dig into the actual assembly program. I initially dug into assembly on the Commodore 64 using the 1980s Turbo Assembler program on my actual C64. This worked fine, but once I discovered the amazing CBM PRG Studio for Windows, I never looked back. It's hard for a longtime PC programmer to switch keyboard layouts from the PC keyboard layout to the Commodore layout. Plus, CBM PRG Studio makes rapid development and debugging of these programs as easy as Visual Studio does for Windows development. Comments in many assembly files usually start with a semicolon. You'll know all the red text in the file are comments I've made. Take a look at lines 6 through 8. This is a trick used by many a developer for the C64 over the years. It simply writes a single line of BASIC to the CBM BASIC interpreter's program memory that allows the user of your program to simply type run to start your program once it has been loaded from floppy disk. At line 6, we tell the assembler to store the next command starting at hexadecimal or base 16 number, memory location 0801. All memory locations are usually referenced by their hexadecimal or hex location in most 6502 assembly programs. Line 8 then writes this row of byte data into memory starting at 801. The resultant BASIC is 10 sys 4096 as seen in the comment at line 4. Speaking of sys 4096, how is it those sys commands started programs and games on the C64? We'll take a look at line 10. This line tells the assembler to place the next part of the program in memory at hex 1000 in the C64's memory map. Translating from hexadecimal to decimal numbers, 1000 hex is, you guessed it, 4096 in decimal. Line 14 uses instruction JSR. JSR means jump to new location saving return address. It is the equivalent of the sys command in BASIC, really. The kernel, the built-in ROM in the C64 that is the closest thing it has to an operating system, essentially contains a ton of functions we can leverage for various tasks. And here at line 14, we are calling for the kernel routine that clears the display. Once this is executed, we are returned to the next location in our own program, and it will then execute line 16. Line 16, we utilize instruction LDA. LDA means load accumulator with memory. There are equivalent commands for the X and Y index registers, LDX and LDY. You can load the accumulator, or a few more ways than you can load the X and Y registers. We're going to hit on 3 ways we read and write memory and the processor registers in this program: immediate, absolute, and absolute indexed. Here on line 16, we are using the immediate method. If you're familiar with other high-level programming languages, this is essentially setting up A as a constant. Since the registers and memory locations can store one 8-bit byte, your constant can be a hex value between 0 and FF, which in decimal translates as 0 to 255. So how do we know we're using the immediate method to load A? By the pound sign or hashtag in front of the dollar sign. This tells the assembler that we are assigning the absolute value indicated after the dollar sign as the number we want A to contain. If we only had the dollar sign and a 2-digit hex number, the assembler would think we were trying to load from 0-page memory, which we're not covering today. And if we had only the dollar sign and a 4-digit number, the assembler would assume we are referring to a memory address location. Next, lines 19 to 24, we are setting up the memory locations I have chosen to utilize to store our place value digits. Remember how we loaded 0 in the A register above? We now use STA, or store accumulator memory, to set these 6 memory locations to 0. Running STA does not modify A, it simply places the value currently stored in A in the memory location you specify. This is an example of absolute addressing. We tell the assembler to write what is in A directly to the memory location specified. We start getting to work on our actual program in this next section, lines 29 to 34. This section of code will affect the VIC-2 chip, which is the chip in the C64 that generates the television display and some other things. There are 2 memory maps regarding the screen as we are utilizing it. The screen memory map has a byte for each display position in the normal text mode the machine starts up in, and the color memory map controls what color each of these locations are. The display map essentially is loaded with the hexadecimal equivalent of any character you wish to display from the Petsky character set, and the color memory map sets the color. We are setting the color white for the first 6 characters starting at the top left of the screen. We have a lot of important 65.2 assembly concepts to cover in this small section as well. Breaking this section down starting at 2930, we now load A with a 1. Then we load the X index register to 0 by using LDX. Line 31 has 2 new concepts happening. First, the color LP is a label. We can jump back to here from another point in the program, not unlike a line number in BASIC that we can jump back to with a goto. We'll be using this line as the start of a loop. Next, we have our first example of absolute indexed addressing. Remember how we mentioned that the X and Y registers are index registers? You're about to see why. The STA we see here will start at D800, the location of the top left character's color byte in the color memory map. Initially, X will be 0, so STA will write the contents of A. Currently, a 1 is set on line 29 to D800. On the next line, we see the instruction INX. INX means increment index X by 1. In a single instruction, we've added 1 to X, which was 0, so now the X register contains a 1. On the next line, we see the instruction CPX. CPX means compare memory and index X. The CPX is followed by an immediate of 6. This is essentially the operational equivalent of the first half of an if statement in BASIC, or if X equals 6. What about the then portion? For that, we have to head to the next line and the B&E instruction. B&E means branch on result not 0. This requires a little explanation. Let's go have a look at the 6502 programming model again. Basically, if the value loaded in X when the CPX instruction is ran matches the value we ran with CPX, CPX sets the 0 processor status flag, indicating that X and the compared value match. Otherwise, the 0 flag is off. If the 0 flag is off, B&E will branch execution back to line label color LP, forming a simple loop. So each pass of this loop, X is incremented one more time, and each time line 31 is ran, we write a 1 from the accumulator to memory location D800 plus X, until we've written address locations D800 through D805 with a 1, setting them all to the text color white. These positions will remain white for the remainder of our program, as these VIC2 registers will remain set at white until we power the C64 down or change them again within our program. Now we're to the workhorse part of our program, beginning at line 36. This 1's label is a bit misnamed. It was a leftover from an earlier attempt at the program, but it came in handy for this version, and I'm too lazy to change it. I chose to use the Y index register for this next short loop. This loop is very similar to the color memory map loop, but this one is what writes out the actual numbers to the display. So, at 38, we initialize the Y index with a 0. Our 6-digit display is stored in 6 bytes beginning at location 8002, so in line 39 we load the accumulator with LDA with 8002 offset by the value in Y. Line 40 utilizes ORA, or memory with accumulator. This is the one command in this program that I'm not sure about regarding how this works. I just know that running this against our current digit loaded in A from memory converts its value to its proper Petsky character mapping for the digit we want to display. If I recall, I believe I saw this in an old magazine or book from the 1980s that had been scanned online somewhere. Line 41 stores the Petsky converted value in A to the display registers of the VIC2 chip. The top left character position is at 0400, so we store what is now our display character in the accumulator to that memory location offset by Y. And at line 42, we increment Y by 1. Lines 43 and 44 make up the rest of the display loop. 43 compares the value of Y to 6. If it matches, the 65020 flag is set. 44 branches back up to disp LP at line 39 to display the next value in the next column on the screen, unless Y contains a hex 6, then we continue on to line 48. By now, what we see in line 48 is self-explanatory, hopefully. We're loading the accumulator with 0 to reinitialize. The comment above it helps tell you why. Starting at line 51, and for most of the rest of the program, we are now implementing the same basic logic we formed with our if statements in the Quick Basic program, where we fall through each place value and compare if we've reached 10 at each one. If we don't, we increment the current place value by 1, and then branch all the way back up to line 36 in order to update the display, each increment by 1. So, as you can see by the comments, lines 51 to 55 deal with the 1's column in memory, and we work our way to the left in memory. So we start at RAM byte 8007, loading the hex value stored there into the X register. We then increment X by 1. We then store X back into 8007. Next, we compare X to the hex number A, which is equivalent to decimal number 10. If X is not equal to A, we branch up to the 1's label again, update the video display, and run through it all again. However, if X is equal to A, we continue down to line 58. Up on line 48, we keep our accumulator set to 0. This causes the STA on this line to set our 1's position to 0, as we can only display 0 to 9 here, of course. Then we load X with the 10's place value from RAM location 8006, and then we follow the same increment store check process from line 60 to 62. This cascading logic continues looping until we reach the 100,000's place value check at lines 97 and 98. Essentially, as soon as the 100,000s becomes 1, we jump on down to line 102 and update the display one more time with a display loop at final disp, line 103. Line 110 contains an RTS, which is a final command we have not seen in the program, and indeed is the final command. It means return from subroutine, and in this case, execution stops and the C64 will return control to CBM Basic. Now, the moment you've all been waiting for. Which is faster, Basic or Assembly? Little background here, we ran each program on actual Commodore 64 hardware, not an emulator. Both programs were ran on the same unit, with the video output captured with composite video capture gear. Then we synced the clips together at nearly the exact same moment run was entered to kick off execution. Here we go. Amazingly, you can see that the assembly program reached 100,000 in only about 13 seconds. It reached that value at about the same time the basic program reached 390. So, why is the assembly program so much faster than the basic program? The short answer is clock cycles. Essentially, every keyword or command in CBM Basic corresponds to an entire assembly program that implements its functionality. So every line of your basic program, it has to interpret what you need, jump and run a program, and jump back, which eats a lot of clock cycles on the 6502. Our assembly program uses far fewer clock cycles and very precisely moves data around in memory, so it is many, many times faster. Essentially, the processor has a lot less to process the way we've written our assembly program, versus the processor having a lot more to process when it comes to executing the interpreted code of the basic program. Even each individual 6502 opcode takes a certain amount of clock cycles, as you can see here in the last column of each of these tables in the C64 Programmer's Reference Guide. Using different memory addressing methods can use even more clock cycles than others on each individual opcode. Take a look at lines 38 to 44 here. This is the loop that updates the C64's display every time a number changes. This runs every time a digit changes. The sum of all the 6502 cycles utilized is 19 cycles, and that's 19 times 100,000, or 1,900,000 cycles of the 6502 processor per digit update. 6 digits are displayed, so the cycles used per increment for this code alone total 11,400,000. Let's run one more test by modifying our assembly program. If we move the ones label from here to here, we will only execute the display loop at the start of the program, and the display loop at the bottom of the program where it will execute once 100,000 is reached. This will save us literally millions of clock cycles. Let's run this on the C64 hardware and compare it to the original program. As you can see, this cuts down our overhead in the program so much that the program runs in 2 seconds instead of 13. In fact, we have time to run it over and over a few times. Thanks for hanging out with us here on 3 Old Tech Dudes. Please subscribe to us here on YouTube for more tech old and new, tinkering at the workbench, repairs, ham radio, electronics, computers, and more. Please like this video and share 3OTD with your friends to help us grow the channel. We tweet at 3 Old Tech Dudes 1 on Twitter, and you can keep up with us on Facebook. Just search for 3OTD and look for our logo. Thanks so much for watching.